Hello everyone, my name is Subrata Samanta and I am a tutor for the physics subject. So in the previous class we will started a problem that is to calculate the electric field due to a uniform charged disc. Okay. So we will continue this problem in this class. So the problem is that a uniform charged disc of radius r with a total charge q that lies in the xy plane okay, and find the electric field at a point P along the z axis that passes through the center of the disc perpendicular to its plane. So, find the electric field at a point P. Okay. So, we will draw a diagram where the point P is indicated. Okay. So, let us first draw a disc in the xy plane. So, we choose a coordinate system x, y and z, okay, 3D coordinate system, and we consider a disc in the xy plane, okay, at the center at origin. Okay, this one is the origin, and this is the disc. Okay. It is not a ring, okay, it is a disc, and we calculate the electric field at point P. So, we denoted the point P on the z axis and the distance from the origin is z. Okay. So, in order to calculate the electric field at point P, so in the as same in the previous problem, so we first consider a small strip. Okay. So, in this case we consider a ring. Okay. So, we consider a ring, concentric ring. So, concentric means that, so we consider a concentric rings, that means the center of the ring and the center of the disc must be coincident. Okay. So, let us consider a concentric uniformly charged disc. So, let us consider a concentric uniformly charged rings, right. Charged ring, okay, and the discs, okay, can be treated as a set of concentric uniformly charged rings, right. So, similarly, if we for in the case of linear charge density problems, we consider a rod, okay, and in this rod we consider a strip, right. So, this one, and the rod can be treated as a set of strip, right. So, similarly, for a disc problem we consider a ring, okay, and the full disc can be treated as a set of concentric charged rings. So, just this 1D problem mapped to a 2D problem, okay, in the same way. So, what is the charge of this concentric ring? Okay. So, the charge, so ring and concentric ring and has a charge dq becomes sigma times 2 pi. So, let us denote the radius of this ring r prime, okay, and the strip is, sorry, the width of the ring is dr prime, okay. So, r prime dr prime. So, this is the smallest distance, and since dr prime is very small, so we consider this one is a ring, okay, but it is actually finite width. Okay. So, if we so now so here the sigma is a surface charge density, okay, and that is uniform. So, it is specified in the question, okay, for sigma surface charge density and which is uniform. Okay. So, that is why you consider a uniform charged ring, okay, because sigma is uniform. So, if sigma is dependent on R, okay, then so then again the uniform charged and the concentric charged ring, it depends on also R, okay, the dq is also depends on R, but in this case the problem is simple, okay. So, we take the uniform charge distribution. Okay. So, now we calculate the electric field at point P. So, again by symmetry arguments. So, if we denote the distance from, so from this point, so consider the distance from this, so at any point from the ring, okay, to the point P is R, okay, and the angle is theta, and as you see in the previous problem that in case of ring, okay, the electric field at the point P has only z component, okay. So, other components become vanishing. So, in this case the electric field at point P these directions. So, these directions, okay, and similarly for the opposite to this point, okay, due to this point the electric field these directions, okay, and the only non-zero component is the z component. So, this component become vanishes. Okay. Similarly, if you consider all the contributions from the ring, okay, so the remaining non-zero component is the z component. Okay. We already see in the case of ring problem. Okay. So, then the electric field, and we use the result for the case of ring. Okay. So, that is why we developed a systematic way that first we calculate the electric field due to a line charge density, and then we bending this line into a ring, okay, and then we calculate the disks, okay, such that the we use always the previous results. Okay. We know that the, so we know the electric field at point P due to ring, due to charged ring, okay, with charge dq, okay, is. So, you already know we calculated this in the previous class. Okay. So, dEz, so only z components, and this one is 1 over 4 pi epsilon naught z dq, right. So, the distance times dq, since that this ring now the charge is dq, okay, and the corresponding electric field is dEz. Okay. So, the only difference is that, so r prime square z square is 3/2. So, only difference is that the charge is dq. Okay. So, if the charge is q, then the total charge is q, then the electric field is Ez, okay, in the case of ring. So, this one becomes 1 over 4 pi epsilon naught. Now, we put the values of dq. So, z times sigma 2 pi r prime dr prime, right, by r prime square plus z square to the 3/2. So, now what is the limit of r prime? So, the limit of r prime, so if you look into the figure, so we consider a charged disc of radius r, right. So, that means this radius is r, okay. So, the limit of r prime then 0 to r, okay. The limit of r prime becomes 0 to r, okay. So, therefore, the electric field at P, okay, we integrate over the r prime, okay. So, the total electric field at point P is Ez, so is the integrate over dEz, right. So, first we consider a small element, and we calculate the electric field due to this, okay, and then we integrate. So, this becomes just plugging into this. So, sigma z over 4 pi cancel. So, 4 epsilon naught, right, times 0 to r prime dr prime, okay. So, this 2 also cancel. So, this one is 2 epsilon naught and then r prime square z square 3 by 2, okay. So, now we, so in order to solve this integral we change the variable, okay. So, choose the variable u, new variable, this becomes r prime square plus z square, okay, and this one is u, okay. So, then du, so z is constant, okay, I think. So, in this case z is a fixed distance, okay. So, you consider z as a constant, okay, for a fixed distance, for a fixed point p from the center to a fixed point p. So, z is constant. So, then du becomes 2 r prime dr prime, okay. And so, now what is the limit of then? So, when r prime equals to 0, this implies that u z square, and when r prime r, u is r square plus z square, right. So, now the limit is changed, and the integral becomes, so Ez, so the integral becomes sigma z over 4 epsilon naught, okay, times z square by z square plus r square, right, and then integrate over du by 3 by 2, right, okay. So, now this looks like a simple expressions, okay, in terms of u, and we also change the limit of the integrations. So, then it is easy to solve this integral, okay, just you know that what is the result of these integrations, okay. So, sigma z over 4 epsilon naught times u to the power minus half divided by minus half, right, and the limit is z square to z square plus r square, upper limit and lower limit. So, finally got this minus sigma z over 2 epsilon naught 1 over root over of r square plus z square minus 1 over z square, right. So, now the interesting is that, so sigma over 2 epsilon naught, right, by, so multiply with the minus sign. So, this one comes first. So, 1 over, sorry, z over mod z. So, this mod is important, okay. So, whenever taking a square root of z square, it has become a plus z or minus z, okay. So, in principle this is the mod z, and minus z over r square plus z square in the square root, okay. So, remember this mod sign is important, okay. So, this is the result, okay. So, now, so this result can be written separately for z greater than 0 or z less than 0, because in this case we choose z from the origin to the z axis, right, but in principle z can take in any directions, negative or positive, okay? So, this result is independent of the direction, okay, positive or negative. So, for z greater than 0, Ez is, so now for z greater than 0, the mod z value is z, right. So, sigma over 2 epsilon naught times 1 minus z by square root of r square plus z square, and for z less than 0. So, now in this case mod z value, so mod z value becomes minus z, right. So, then the Ez sigma over 2 epsilon naught minus 1 minus z over square root of r square plus z square. So, this mod z actually encoded the the directions. Okay. So, if we take z less than 0, that means the below the plane of the charged disks. Okay. So, below the plane of the charged disks or the above point, any point. Okay. So, the interesting point that if we calculate the difference between these two values of Ez, okay, so there is a finite discontinuity. Okay. So, that means, okay, so we will come into this point. So, first plot these expressions as a functions of z. Okay. So, we plot this. So, we plot Ez over E naught. Okay. So, we make a dimensionless variable and z over r, right. So, for the E naught, it sigma over 2 epsilon naught, right, and again we divided by r. So, we make a dimensionless variable and the plot looks like, so the electric field looks like this and this at 0, that means that z equals to 0, we have seen that there is a finite discontinuity. Okay. So, this is the discontinuity. So, suddenly jump from positive to negative value. So, Ez suddenly jump positive, so positive to negative value. So, there is a finite discontinuity. So, that means, so this is the negative direction. So, this one is a negative direction, this one is a positive direction. Okay. So, the physical is that, so when you calculate the electric field above of the charged disks, okay, and when you calculate the electric field below of the charged disks, okay, and you cannot continuously above of the disks to below of the disks. Okay. So, there is a finite discontinuity. Okay. So, the electric field cannot same as the above and the below limiting cases. Okay. So, we will discuss this in the next class in a more details, and also we consider some limiting case. Okay. So, where the z is very greater than equals to r, very greater than r, or r is very greater than z. Okay. So, in that limiting case we will consider in the next class. Thank you.